Now we get into the good stuff, which is the limit definition of the derivative. This is the foundation for what this entire course is based off of. So it's really important to go over it now here at the end of the semester. We started with the thought, well, first we had to define what a derivative is. And it all comes down to slope. Slope is rate of change. And we've been working with slope from the very beginning of the semester, and really you've been working with slope since middle school. Our question was, how do we find the slope at a point? That tangent slope, that instantaneous rate of change. But we know you need 2 points to find slope. And so that's what we started the semester with. We were trying to find the slope at 1 point. But all we really knew was how to find the slope between 2 points. So we picked another point, and let's say that it's h away from the point that we want to find the slope at. So this is the point, or the x value, x plus h. We started out not by finding that instantaneous rate of change at x, but with something that we knew, which was the average rate of change, or secant slope, between these 2 points. We know how to find the slope between 2 points. It's just delta y over delta x, or y2 minus y1 over x2 minus x1. So let's do that for this function, which we'll call f. We'll start with y2. This y value right here, well, that's just f of x plus h. And then we're going to subtract off y1, which is this y value right here. Well, that's just f of x. And then we'll divide by our change in x, which is x2, x plus h, minus x1, for x. And it's not hard to see we can do some nice simplifying here and turn x plus h minus x, the x's cancel out, and we're just left with h. That's how we find average rate of change, or secant slope, the slope between 2 points. What we were interested in, however, was not this average rate of change between these 2 points, but the instantaneous rate of change, or the tangent slope, at x. We can't do delta y over delta x if we only have 1 point. There's no change at all. If you look here, we can't actually let h be 0, because then we'd get 0 over 0, which is an indeterminate form. So we can't actually let h be 0. We can't actually make this distance nothing. But what we can do is get h really, really close to 0. Get these points infinitely close together, and then look at the limit as h goes to 0 of this difference quotient. And looking at that limit, looking at what that secant slope is approaching, will tell us that instantaneous rate of change, or the tangent slope, at the point x. This is so important. So if you haven't written anything down this entire class, write this down. The derivative of a function, which we call f prime of x, equals the limit as h goes to 0 of f of x plus h minus f of x over h. It is just the limit as the 2 points on that secant slope become infinitely close together, turning into 1 point. The AP exam really loves using this limit definition of a derivative to see if you understand that fundamental concept of calculus. And so they like to give limit problems like this. Now we could FOIL all that out, factor it, divide out the whole, and use direct substitution. But I really have no desire to FOIL x plus h out 8 times. And that's not what the AP exam wants you to do either. What they want you to do is look at this structure and recognize that it's the limit definition of the derivative of some function. And our goal is to figure out what that function is. We see that this is f of x plus h minus f of x all over h, meaning that the function itself, f of x, is 3x to the 8. We can take the derivative of that really easily using power rule. We can just bring the 8 down and get 24x to the 7th. That is the derivative of 3x to the 8. So that's what this limit equals, 24x to the 7th. Really easy to evaluate that limit just by recognizing the derivative. You also might have a problem that looks like this. The main difference between these two problems is that there's no x in this second problem. They're asking us to differentiate a function and then plug in a value for x. So our goal here is to figure out what x value we're supposed to plug in and what function we're differentiating. If this is f of x plus h minus f of x in the numerator, it's pretty clear to see x equals 2. Our next step is to figure out what function we're actually differentiating. This function, now that we've plugged in 2, has sort of lost its form over on the 16. But if we look at f of x plus h, we can see that structure is 4 times x plus h squared, which means our original function is 4x squared. We can check and see that that's equivalent if we plug in 2 to 16. And so what we have to do is differentiate it, and we get 8x. And now we can plug in 2 to our derivative and get 16. So this limit actually equals 16.